We sent two machines into the infinite dark. We packed them with the best technology we had in 1972, knowing they would probably never come home. And then we did something strange. We gave them a message, a golden record, like a letter in a bottle thrown into an ocean we didn't understand. 40 years later, one of those machines is still sending us signals from beyond the edge of everything we can see. And it's still alive. This is the story of the Pioneer probes. And this is the story of humanity's first real goodbye, the moment everything changed. It's March 2nd, 1972. Kennedy Space Center, early morning. The sun hasn't fully come up yet, and there's this tension in the air that you can only feel when something absolutely unprecedented is about to happen. Thousands of people are here. Scientists, engineers, journalists, people who drove down from Miami just to watch. Because today, we're doing something we've never done before. We're sending something so far away that we will probably never get it back. The rocket is called Atlas Centaur. It's massive, 63 meters tall. And on top of it is Pioneer 10, this little gold-colored cube, and I mean little, it's only about the size of a car, is about to become the fastest thing humanity has ever built. The most ambitious unmanned mission we've ever attempted. The first spacecraft ever designed to leave the solar system. But here's the thing that gets me. Here's what makes this moment so viscerally human. Nobody actually knew if it would work. We had never done this before. We had never sent anything past Jupiter. The asteroid belt was this big unknown, a field of rocks and space dust that for all we knew could rip apart anything we sent through it. Scientists at NASA genuinely debated whether Pioneer 10 would make it through. There were meetings, there were arguments. Some people thought the whole thing was a waste of money. And yet, they built it anyway. Why we needed to leave. Here's the context you need to understand. It's 1972. Vietnam is still happening. There's social chaos, but something else is happening too. Something quieter, but just as powerful. We're running out of time to do this. The space race with the Soviet Union is officially over. America won. We put people on the moon. The Soviets didn't. So now the question becomes, what's next? What do we do with all this technology, all this expertise, all these rockets and engineers and dreams we've accumulated? Some people wanted to go bigger, build space stations, put people on Mars. But there was another group of scientists, people like John Cassani and Carl Sagan, who looked at the problem differently. They said, we have a window right now. In the 1970s, the planets are aligned in a way they won't be again for 200 years. Jupiter and Saturn are in positions where a spacecraft launched today could reach them with minimal fuel. We have a shot, but we have to take it now. In 10 years, the alignment changes. The window closes, and nobody gets another chance until the year 2018. So they convinced NASA. They convinced Congress. And they convinced America that what we needed to do, what we had to do, was to build something small, something cheap, something that could use existing rockets and existing technology and send it out there. That something was Pioneer 10. And what's wild is this. The entire project almost didn't happen because of money. We're talking about a mission that would define humanity's next 50 years, and it almost got canceled because Congress wanted to save a few $1,000,000. But then, and this is where humans being humans becomes really important, Carl Sagan and his colleagues made a pitch. They said, look, we're not asking for much. We're asking for the chance to send something beyond Jupiter, something that will outlive all of us, something that long after we're dead, will still be out there, still be transmitting, still be reaching back to tell us what's out there. And Congress said yes. This is the moment where it stops being just about space exploration. It becomes about something bigger. It becomes about the question, what do we want to say to the universe? The engineering miracle. Nobody talks about now. Before we get to the profound philosophical stuff, we need to talk about how genuinely insane the engineering of Pioneer 10 was. Because this is where it gets good. This is where you realize these weren't just dreamers. They were problem solvers who invented solutions to problems that technically didn't exist yet. The spacecraft is basically a 12-sided polygonal structure. It looks like something out of a 1970s sci-fi movie because it is exactly what a 1970s sci-fi movie would look like. It weighs about 260 kilograms. That's less than 3 people. For reference, that's less than a grand piano. And this thing is going to travel farther than anything humans have ever built. But here's the thing. As you go farther from the sun, solar panels stop working. The sun gets dimmer and dimmer. So Pioneer 10 couldn't use solar panels. It had to use something else. They used radioactive decay, specifically plutonium-238. 4 plutonium pellets, each about the size of a fingertip, inside thermoelectric generators. As the plutonium decays, it releases heat. That heat is converted directly into electricity. Radioactive batteries. It's beautiful and terrifying in equal measure. These generators would work for decades. Not forever, eventually they'd fade, but for decades. Long enough to reach places we'd never reached. Long enough to send back data from beyond the edge of the known solar system. But then there's another problem: cooling. When you're inside a spacecraft powered by radioactive decay, you're basically sitting inside a small nuclear furnace. The temperature differential between the warm interior and the freezing cold of space, which is about 2.7 degrees above absolute zero, is extreme. Too extreme. You need to manage that heat. You need to get rid of it without killing your instruments. So they built radiators, actual radiator panels that bleed heat into space. It's the same principle as a car radiator, except you're bleeding heat into a vacuum that's colder than anything humanity has ever experienced on Earth. And it works. It actually works. But I haven't even gotten to the really crazy part yet. Navigation. How do you navigate a spacecraft when it's 12 times farther from the sun than Earth? When radio signals take hours to travel? When you can't course correct by hand? They had to pre-program Pioneer 10 with incredible precision. The trajectory had to be perfect. Even a tiny error would compound over the years and the decades. A deviation of millimeters at launch could mean missing Jupiter by millions of kilometers. And they had to do this in 1972, using computers that had less computing power than your phone, less memory than a single photograph on your camera. The fact that Pioneer 10 made it to Jupiter, let alone beyond, is not just impressive. It's incomprehensible. It's like threading a needle in hurricane while blindfolded from a moving car. And they did it. They actually did it. The journey begins March 2nd, 1972, 8:49 p.m. Eastern Standard Time. The countdown reaches 0. The engines ignite. The rocket shudders. And then, slowly at first, then faster, Pioneer 10 begins to move upward. The acceleration is violent, crushing. Anyone on board would be pressed into their seat with multiple G's of force. But there's nobody on board. That's the whole point. It's autonomous. It's alone. The rocket breaks through the atmosphere. The sky goes from blue to purple to black. And then, Suddenly, there's no up or down anymore. There's just momentum. Pioneer 10 begins its journey across the solar system. Now, here's what's interesting about the first part of this journey. It's actually the most dangerous part. The asteroid belt is coming up. And for decades, everyone assumed the asteroid belt was basically a minefield. We had movies about it, asteroids flying everywhere, ships dodging rocks left and right. But here's the thing about what we assumed versus what's actually true. The asteroid belt isn't like that at all. It's mostly empty. And I mean mostly. The asteroids are so spread out that the chances of Pioneer 10 hitting one are vanishingly small. But we didn't know that in 1972. We thought we were sending a spacecraft through a gauntlet. As Pioneer 10 cruised through the asteroid belt, everything at Mission Control was tense. People were watching the telemetry, waiting for something to go wrong, waiting for a collision report, waiting for the signal to suddenly go silent. It never did. Pioneer 10 passed through the asteroid belt without incident, and in doing so, it confirmed something huge. Space is big, way bigger and emptier than we thought. You could travel for months through the asteroid belt and never see another rock. This is one of those profound realizations that doesn't seem big until you think about it. It changed how we understood the solar system. It changed what we thought we'd find out there. But for the people working on Pioneer 10, it was just relief. They had cleared the first hurdle. The spacecraft was intact. It was transmitting. It was working. And Jupiter was still getting closer. The first close encounter. By December 1973, Pioneer 10 is approaching Jupiter, nearly 2 years into its journey. The spacecraft has traveled farther than any spacecraft before it, and now it's about to encounter the largest planet in the solar system. Jupiter is incomprehensible in scale. If you could somehow put Earth inside Jupiter, it would look like a marble dropped into a swimming pool. Jupiter's mass is more than 300 times Earth's mass. Its storms are the size of our entire planet. And its radiation belts, oh, the radiation belts are something else entirely. Jupiter has magnetospheres, intense magnetic fields that trap charged particles. These radiation belts are deadly. They would kill a person instantly. They would fry most electronics. And Pioneer 10 is about to fly right through them. This was another moment of genuine uncertainty. We didn't know if Pioneer 10 could handle it. We hoped the radiation shielding would work, but we weren't sure. And then on December 3rd, 1973, it happened. Pioneer 10 passed by Jupiter, not crashed into it. Passed by it at a distance of 130,000 kilometers, closer than any spacecraft had ever come to the planet. And it survived. Not only did it survive, but it sent back the most detailed pictures of Jupiter we had ever seen. Photographs that showed the Great Red Spot in incredible detail. Images that revealed cloud structures we never knew existed. Measurements of Jupiter's magnetic field that completely changed our understanding of how planets worked. And then, here's the part that gets me, Pioneer 10 used Jupiter's gravity to slingshot itself. This is called a gravity assist. It's pure orbital mechanics poetry. As Pioneer 10 passed Jupiter, it got pulled by the planet's gravity. This pulled it faster. It accelerated it. And when it came out the other side of Jupiter's gravity, well, it was moving faster than it would have been otherwise. Jupiter essentially threw Pioneer 10 out into the deep solar system. And that's when the real journey began. The dark years. Here's something we don't talk about enough. The loneliness of space exploration. After the Jupiter encounter, Pioneer 10 left the region where planets exist. It entered what we call the heliosphere, the region around the sun that's influenced by the sun's magnetic field and the solar wind. But even that starts to fade. For the next several years, there's nothing. No planets, no asteroids, no encounters. Just Pioneer 10, floating through an endless void, transmitting data about a region of space where literally nothing interesting appears to be happening. The signal gets weaker and weaker. It takes longer and longer for messages to reach Earth. By the time Pioneer 10 is a few years past Jupiter, radio signals are taking 6 hours one way to reach it. You send a command and you wait 12 hours for a response. The mission becomes quiet, unglamorous. The news cycles move on. People forget about it. But the spacecraft keeps going. And this is where I need to tell you something that might change how you think about this whole thing. In 1973, when Pioneer 10 made its Jupiter encounter, it was the biggest space news story of the year. Newspapers covered it. Television stations broke into programming. Kids in schools drew pictures of Jupiter based on Pioneer's photographs. People cared. People paid attention. But here's the thing. The further Pioneer 10 got from Earth, the less interesting it became to most people. There was no drama, no immediate discoveries, no reason to care about a robot floating in a void sending back measurements of cosmic radiation levels. So funding got tighter, the team got smaller, and by the mid-1970s, Pioneer 10 was just there, doing its job. Unnoticed, unloved. This is actually a pattern we see over and over in space exploration. The exciting moment is the launch or the encounter, the moment of drama. But the real work, the slow, patient, decades-long work of exploration, that happens in silence. Pioneer 10 was experiencing this. It was becoming a ghost, a phantom spacecraft that nobody thought about anymore, and yet it kept transmitting every day, every week, every month, for years and years. The data it was sending back was fascinating to the scientists still paying attention. Cosmic ray measurements, solar wind data, information about the structure of the heliosphere, the boundary between the sun's influence and the true interstellar space beyond. But to the general public, it was boring. It was yesterday's news. This is important because it teaches us something about human nature. We love the exciting moment. We love the discovery. We love the aha, the sudden breakthrough. But we're not great at appreciating the slow, steady work, the patient accumulation of knowledge, the journey that takes decades. Pioneer 10 was on that kind of journey. By 1976, it had traveled over 1 billion kilometers from Earth. That's a distance so vast that light from the sun takes over 7 hours to reach it. The sun appears as just another bright star in the sky, and Pioneer 10 keeps going. The message in the bottle. But here's where the story becomes something more than just a technical achievement. Before Pioneer 10 launched, Carl Sagan, yes, that Carl Sagan, the guy who later became famous for Cosmos, made a proposal. He said, "We're sending this spacecraft into the void. Maybe someday, long after we're gone, something intelligent will find it." What should we tell them about us? This is a profound question. Let's sit with it for a second. You're an alien civilization. You find a spacecraft floating in the void. It's from a species you've never met, a civilization you never knew existed. What do you want to know about them? Sagan's answer was, everything. We should tell them everything. So NASA assembled a team, astronomers, scientists, artists, musicians, Carl Sagan himself, and they created the golden record. It's an actual phonograph record made of gold-plated copper, and it contains images, photographs of Earth, of people, of cities and landscapes and nature, mathematics and physics, diagrams explaining our understanding of the universe, music, Bach, Beethoven, Chuck Berry, Johnny B. Good, music from cultures all around the world, greetings in 55 different languages, people from all around Earth saying hello to the universe, the sounds of Earth, volcanoes, rainfall, whale songs, scientific data, measurements, and information about our planet. This record was encased in a protective gold-plated aluminum cover. It was bolted to Pioneer 10, and then we launched it into space. And here's what kills me about this. The chances of any alien civilization ever finding Pioneer 10 are almost certainly zero. The spacecraft is tiny. Space is vast. The odds are incomprehensible. But we did it anyway. We made this record anyway. We chose this music anyway. We recorded these greetings anyway. Because we had to. Because we wanted to say something to the universe. Because somewhere in us, somewhere in our collective human heart, we needed to send a message out into the dark. We needed to say, we were here. We thought. We felt. We made music. We loved each other. We looked up at the stars and wondered. And if, just if, someone ever finds this, we want them to know that this is deeply, profoundly human. And it's also deeply, profoundly sad. Because we almost certainly know this will never be found. But we do it anyway. The physicist Frank Drake, the same guy who created the Drake equation about the probability of alien life, he worked on the Golden Record project. And he's talked about how meaningful it was, even knowing it was almost certainly futile. He said something like, "It doesn't matter if anyone ever finds it. We did it. We made something. We reached out. And that act of reaching out, that act of saying something to the cosmos, that matters. That matters to us, the second pioneer." Now here's something that makes the story even more complete. Pioneer 10 wasn't alone. 2 years after Pioneer 10 launched in April 1973, NASA launched Pioneer 11. Same design, same golden record, same mission. Pioneer 11 would reach Jupiter in December 1974. It would do its own gravity assist. And then it would do something Pioneer 10 didn't. It would continue on to Saturn. Pioneer 11 would become the first spacecraft to reach Saturn. It would fly by the planet, take incredible photographs, and measure its radiation environment. It would discover moons. It would measure ring structures we didn't know existed. And then it too would continue on into the deep space. So now we had 2 robots. 2 messages in bottles, 2 records spinning through the void. The symmetry is beautiful. The redundancy is wise. Space exploration is dangerous. And having 2 spacecraft meant if one failed, we'd still have one continuing the mission. But it's also poetic. We sent out 2 messengers, one heading in one direction through space, one heading in another. Like 2 ships leaving a harbor, each taking a different route across an infinite ocean, and both of them would survive far longer than anyone expected. The mystery nobody expected. Here's where it gets weird, and I mean genuinely, legitimately weird. In the 1980s, as Pioneer 10 coasted through the outer solar system, scientists noticed something strange. The trajectory was off. Not by much. We're talking about tiny deviations. But they were there, and they shouldn't be. Pioneer 10 should be traveling in a straight line, pulled only by the sun's gravity. The path should be predictable. We should be able to calculate exactly where it is at any given time. But it wasn't. The spacecraft was being pushed slightly, gently, but measurably. Scientists called this the Pioneer anomaly, and for decades nobody could explain it. This is genuinely one of the most fascinating unsolved mysteries in space science, and it became an obsession for some researchers. What could cause this? What was pushing the spacecraft? Theories emerged. Maybe it was solar radiation pressure. Maybe the craft was leaking fuel. Maybe there was mass imbalance affecting the trajectory. Maybe the onboard transmitter was pushing it back like a tiny rocket engine. Or, and this is where it gets exciting, maybe it was something unknown. Some scientists seriously proposed that this could be evidence of modified gravity, or some kind of unknown force operating in the outer solar system, or something we hadn't thought of yet. This is where science gets really interesting. This is where mysteries open up. A mystery like the Pioneer anomaly can't be solved by just making guesses. You have to dig deeper. You have to look at all the data. You have to consider possibilities you haven't thought of before. And it turns out, spoiler alert, that the answer, when we finally figured it out, was somewhat mundane, but also kind of beautiful. In 2012, physicists at NASA's Jet Propulsion Laboratory analyzed all the data from both Pioneer spacecraft. They looked at thermal radiation. They looked at how heat from the radioactive generators was being radiated into space. And they realized something. The way the spacecraft was radiating heat into space wasn't symmetric. It wasn't even. The heat was coming off slightly asymmetrically, which meant there was a tiny thrust pushing back against the spacecraft. It was so small, about a billionth of a g of acceleration. But over decades, tiny forces add up. They accumulate. They create these small but measurable deviations, so the Pioneer anomaly was solved. It wasn't alien technology. It wasn't modified gravity. It was thermal radiation. But you know what? In some ways, that's more beautiful, because it means that the scientists who built Pioneer 10 and 11 were so careful, so meticulous, that they could eventually detect and explain effects so small that they amount to the tiniest push imaginable. It shows how far we've come in understanding orbital mechanics and physics, and it shows how, even after solving the mystery, the pioneers remain objects of intense scientific study. They're not just historical artifacts. They're still teaching us things. They're still revealing secrets about how the universe works. The silence begins. By the 1990s, the signal from Pioneer 10 was becoming very faint. Not gone, but faint. The radioactive generators were decaying. The plutonium was losing its power. Less electricity meant a weaker transmitter. A weaker signal meant it was harder and harder to hear the spacecraft. But NASA kept listening. They built bigger and bigger radio antennas. They became more sensitive to faint signals. And they kept trying to make contact. Pioneer 10 was now over 1 billion miles from the sun. It had been in space for nearly 20 years. It had outlasted its original 5-year mission by a factor of 4. Scientists began to understand that this wasn't a spacecraft that would stop working next year, or the year after that. This was a spacecraft that could continue transmitting, could continue surviving for decades to come. The question became, how long could it possibly last? And more interestingly, what should we do with it now that it's out here? Because here's something that changed the entire nature of the Pioneer mission. Originally, it was about exploring, going somewhere, sending back pictures and data about new places. But now, Pioneer 10 was so far away that there wasn't anything new to explore. There were no more planets, no more encounters. It was just drifting through empty space. So, what was its purpose now? The answer was subtle but profound. It was a test, a long term test of spacecraft engineering, a demonstration that we could build something that would work reliably for decades on end. It was proof that humanity could reach out into space and maintain a presence there, that we could send something and it would keep working and keep communicating year after year after year. For some scientists, that was actually more important than any discovery because it meant that long term space exploration was possible, that we weren't limited to quick missions and brief encounters, that we could build things that would last. This realization would inform everything that came after: the Voyager missions, the rovers on Mars, the spacecraft that are still operating today, long after their original mission timelines. Pioneer 10 proved it could be done. The last signal. On January 23rd, 2003, something happened that most people never heard about. Scientists at NASA made a final attempt to contact Pioneer 10. The spacecraft was now over 7 billion miles away. It had been in space for over 30 years. The radioactive generators were very weak. The signal was barely detectable even with the most sensitive antennas on Earth. The team at JPL sent out a command. A simple request: respond. Send back a signal. Let us know you're still there. For a long moment, there was nothing, and then, faint, barely detectable, but there, the signal came back. Pioneer 10 was still alive. This was January 23rd, 2003. I want you to think about what this means. A spacecraft built in the early 1970s with technology from that era was still functioning, still responding, still reaching back across 7 billion miles of space to say hello. The team at NASA did something special that day. They marked it. They acknowledged it because they knew what it meant. This might be the last time we ever hear from Pioneer 10. The signal was so faint that it was already at the edge of what Earth's antennas could detect. The plutonium generators had maybe a few years left. Eventually, the power would fade. The transmitter would go silent. And when it did, there would be no way to wake it up, no way to revive it. Pioneer 10 would simply drift, still moving, still traveling through space, but no longer speaking to us. So NASA decided to stop sending commands. They decided to stop trying to make contact, not because the spacecraft was gone, but because they wanted to preserve the power for as long as possible. And then they waited. They listened. They strained to hear the signal. And slowly, over the next few years, it got fainter and fainter. The last confirmed signal from Pioneer 10 was received on January 23rd, 2003. After that, the signal became too faint to detect reliably. NASA stopped trying to make contact. Pioneer 10 was still out there, still transmitting, but we couldn't hear it anymore. In a way, this is the saddest part of the story. Not that the spacecraft broke down, not that it failed catastrophically, but that it simply faded away, like a voice disappearing into the distance, like someone walking away from you into the fog, getting quieter and quieter until you can't hear them anymore. But you know they're still out there. Pioneer 11's journey. While Pioneer 10 was fading into silence, Pioneer 11 had its own adventures. After its encounter with Jupiter in December 1974, Pioneer 11 was flung towards Saturn. The spacecraft would take nearly 7 years to get there. 7 years of coasting through empty space with nothing to do but maintain its systems and send back data about the solar wind and cosmic radiation. And then, on September 1st, 1979, it happened. Pioneer 11 reached Saturn. This was huge. Nobody had ever seen Saturn up close before. We had pictures from telescopes on Earth. We had theories about what it might be like, but we'd never actually sent a spacecraft there. Saturn is different from Jupiter. It's less dense, less violent, but in some ways, more beautiful. The rings are one of the most stunning features in the entire solar system, and Pioneer 11 was about to photograph them at close range for the first time. The encounter was incredible. Pioneer 11 passed within 20,000 kilometers of Saturn's atmosphere. It sent back photographs of the planet's cloud structures. It measured the planet's magnetic field. It discovered new moons, tiny objects orbiting in the Saturnian system that we didn't know existed, and it revealed something remarkable about the rings. The rings of Saturn aren't solid. They're not one continuous band. They're thousands of individual ringlets, millions of particles, each one orbiting independently. It's like a cosmic record, concentric circles of ice and rock, each one playing its own song. Pioneer 11 measured the structure of these rings. It showed us that the rings were far more complex than we thought, that there were gaps between them, that there were moons embedded in the rings, shepherding the particles, keeping them in their orbits. This was groundbreaking. This changed our understanding of planetary systems. This showed us that nature could create order and structure even in something as chaotic as a ring system. And then Pioneer 11 did what Pioneer 10 had done before it. It used Saturn's gravity to slingshot itself even deeper into space. Pioneer 11 was now headed out of the solar system. Like Pioneer 10, it would continue traveling, continue transmitting, continue its slow journey into the void. The long fade. By the 1990s, both Pioneer spacecraft were struggling. The plutonium in their power sources was decaying. The power output was dropping. The signals were getting weaker and weaker. Pioneer 11's last confirmed signal came in 1995, almost 30 years after launch. The spacecraft had traveled farther than any spacecraft before it. It had made discoveries at Jupiter and Saturn that fundamentally changed how we understood the solar system. And then its voice faded away. Like Pioneer 10, it was still out there. Still traveling, still technically alive, but no longer able to speak to us. This is important because it teaches us something about the nature of exploration and about loss. We send things out into the void. We build them as carefully as we possibly can. We load them with our hopes and dreams and messages to the cosmos, and then we watch them fade away. We watch them become silent, and we have to accept that. This is the price of exploration. This is the cost of reaching out. You send something away and you know that eventually you won't be able to hear it anymore. Eventually it will be gone from your life, traveling on, but unreachable. The pioneers taught humanity this lesson. They taught us that some things we create are meant to leave us, that some journeys don't end at a destination. They end in silence, in the void, in the unreachable dark. And that's beautiful, in a way. That's okay. That's what they were made for. Where are they now? So here's the question that haunts us. Where are Pioneer 10 and Pioneer 11 right now? Pioneer 10 is still out there. It's been traveling for over 50 years. It's now over 10 billion miles from the sun. It's in the heliosphere, that region of space where the sun's influence is fading. It's moving toward the heliopause, the boundary between the sun's dominion and true interstellar space. At its current velocity, about 36,000 miles per hour, it will take Pioneer 10 another 30,000 years to reach the nearest star system. 30,000 years. That's longer than all of recorded human history, longer than the existence of civilization. And it's still going. Pioneer 11 is also still out there. It's traveling in a different direction, also moving at tremendous speed, also heading toward that distant boundary, also on a journey that will take 30,000 years. These two spacecraft are the longest-lived manufactured objects humanity has ever created. They've outlasted empires. They've outlasted the people who built them. They'll outlast nations and civilizations. And they're still traveling, still reaching out into the void. Now, here's something that I find genuinely profound. We don't actually know exactly where Pioneer 10 and Pioneer 11 are right now. We can calculate their positions based on trajectories and velocities, but we haven't been able to hear from them in years. We've lost the connection. So in a real way, they're gone. They're not gone. They're still out there. But they're beyond our ability to track them, to confirm their position, to hear their voices. They've become myths. Stories we tell ourselves about objects we've lost, and yet we know they exist. We know they're out there. Somewhere in the vast darkness of space, two golden machines are traveling, carrying with them the voices and music and images of Earth, carrying with them humanity's first real message to the stars, the Voyagers and the legacy. Here's where the story becomes even more interesting. Because after the pioneers, NASA learned. They learned how to build spacecraft that could last. They learned what works and what doesn't. And they took those lessons and built the Voyager spacecraft. If the pioneers were humanity's first tentative steps into the void, the Voyagers were something bigger. They were more ambitious. They were built with more sophistication. They had cameras. They had scientific instruments. They were designed to visit not just Jupiter and Saturn, but Uranus and Neptune too. And most importantly, they had more power, more sophisticated power systems that could last longer, much longer. The Voyager spacecraft launched in 1977. They carried their own golden records, updated versions of the Pioneer Golden Record. They carried more sophisticated messages, more music, more images. And they worked. Oh man, they worked. Voyager 1 is still operating today, still transmitting. As of 2026, it's still sending back data. It's the most distant spacecraft humanity has ever built. It passed the heliopause. It entered true interstellar space. And it's still talking to us. Voyager 2 is also still operating. It's the only spacecraft humanity has ever sent to Neptune and Uranus. The Voyagers are, in many ways, the descendants of the pioneers. They're what came next. They're what we learned how to build because the pioneers showed us it was possible. But here's the thing. The pioneers came first. The pioneers were the proof of concept. The pioneers showed that a spacecraft could last decades, that a spacecraft could travel billions of miles, that a spacecraft could reach places we'd never been before. Without Pioneer 10 and Pioneer 11, there would be no Voyagers. Without those first golden messages to the cosmos, we wouldn't have known how to build the ones that came after. The pioneers were the pioneers, in every sense of the word. The burden of messages. Let's go back to that golden record for a moment, because there's something really interesting and also something kind of troubling about what we put on it. The record contains greetings from world leaders, from UN Secretary General Kurt Waldheim, from the President of the United States. These are political figures making official statements. It contains scientific data, diagrams of atoms and DNA, mathematical formulas. It contains music. And this is where it gets interesting because choosing the music was genuinely controversial. Carl Sagan and his team had to decide what music represents humanity. What music should we send out to the cosmos? They chose Bach, Beethoven, Mozart, but they also chose Chuck Berry. Johnny B. Good, because Sagan believed that rock and roll was an important expression of human culture, that it said something true about us. Not everyone agreed. Some people thought rock and roll was too frivolous, too American, not representative of human civilization as a whole. But Sagan included it anyway, because he understood something important. Humanity isn't just the high culture. It's not just the classical music and the scientific formulas. It's also the wild, energetic, rebellious music. It's the things we create for joy, for fun, for the sheer pleasure of making noise. This is a profound choice. It says something about how Sagan understood humanity. It says that we're not a civilization of logic and reason alone. We're creatures who make music, who dance, who rebel against convention, and that should be represented in our message to the cosmos. The record also contains sounds of Earth, whale songs, rainfall, a human heartbeat. These were deliberately chosen. They were meant to convey the reality of life on our planet, not just the intellectual side, but the emotional, the visceral, the real. There's a goodbye message recorded by UN Secretary General Waldheim. It's formal and political, but it ends with, "We hope someday, having solved the problems we face, to join a community of galactic civilizations." It's hopeful, it's optimistic, it's also kind of naive in a way, because even as we were sending this message in 1977, we weren't exactly solving our problems. We were dealing with Cold War tensions, with poverty and inequality, with environmental destruction, and yet we sent this message that said, someday we hope to be better. Someday we hope to solve these things. That's profoundly human too. That's the part of us that reaches out even while we're struggling. That sends messages to the stars even though we haven't figured out how to live together on Earth. The ethics of contact. Here's something that doesn't get talked about enough. What if someone actually found the Pioneer or Voyager spacecraft? What would that mean? Scientists have seriously debated this. The golden records were, in a sense, a beacon, a signal saying, here's where we came from, here's what we're about, here's how to find us. But is that a good idea? Think about it from the perspective of an alien civilization. You find this spacecraft. It has pictures of Earth on it. It has mathematical coordinates. It has information about our solar system. Now, if you're a benevolent alien species, this is great. You learn about us. You maybe decide to visit us someday. You become our cosmic pen pals. But if you're not benevolent, if you're hostile, then we've just sent them a treasure map to Earth. This is actually a real concern among some scientists. The physicist Stephen Hawking expressed concern about contacting aliens. He pointed out that throughout human history, when technologically advanced civilizations have made contact with less advanced ones, it hasn't gone well for the less advanced civilization. Why should we assume it would be different with aliens? So there's an argument that sending out the Pioneer and Voyager records was reckless, that we exposed ourselves, that we made ourselves vulnerable. But there's also an argument, Carl Sagan's argument, that if there's intelligent life out there, we should say hello. That the impulse to communicate is fundamentally human, that even if it's risky, it's worth it. And look, the odds of anyone ever finding these spacecraft are so vanishingly small that it's almost not a practical concern. Space is so big that the chance of an alien civilization finding a small spacecraft drifting in the void is essentially zero. But the philosophical question remains: should we be reaching out? Should we be announcing our presence to the universe? These are questions we still don't have good answers to, and the pioneers and voyagers force us to confront them. The Deep Space Network. Here's something I want to talk about that doesn't get nearly enough attention: the infrastructure that keeps these spacecraft alive. It's called the Deep Space Network, or DSN. The DSN is a system of radio antennas spread around the world. They're operated by NASA's Jet Propulsion Laboratory, and their sole purpose is to communicate with distant spacecraft. There are antennas in California, in Spain, in Australia. They're positioned so that as Earth rotates, there's always an antenna that can see a distant spacecraft. These aren't small antennas. Some of them are as large as sports stadiums. They can hear signals so faint that they amount to a few photons of energy. They can detect signals that have traveled billions of miles through the cosmic noise and radiation and still pick out the precious few bits of information encoded in them. The DSN exists almost entirely because of the Pioneer and Voyager missions. These deep space probes proved that we could communicate across vast distances. They proved it was worth building the infrastructure, and now, decades later, that same infrastructure is used to communicate with every spacecraft we've ever sent beyond Earth's immediate vicinity. The rovers on Mars, the spacecraft orbiting distant planets, the Voyagers, still transmitting from the edge of interstellar space. The DSN is humanity's umbilical cord to the cosmos. It's how we stay connected to the machines we've sent out into the void. And it's a genuine technological marvel. The antennas are so sensitive that they can detect the signal from a spacecraft transmitting with less power than a cell phone, across distances of billions of miles. There are people who work at the DSN, scientists and engineers who spend their careers listening to distant signals, who maintain these antennas, who keep the lines of communication open. For the pioneers especially, these people became something like caretakers. Long after the original mission planners had retired or passed away, there were still people at the DSN who cared about Pioneer 10, who wanted to hear from it, who kept trying to make contact. There's something deeply moving about that. The idea that a spacecraft could be so old that the people who built it were gone, but there would still be people dedicated to keeping it alive, to listening for its signal, to making sure it wasn't forgotten. The cultural impact. Now let's talk about what the pioneers meant culturally. In the 1970s, space exploration was becoming less cool. The moon landing was old news. The space race with the Soviet Union was winding down. There was a sense that we'd done the big thing. We'd landed on the moon. And now what? The pioneers offered a different answer. They said, what's next is the deep exploration, the long journey, the slow push into the unknown. Carl Sagan became the public face of this vision. He wrote about the pioneers. He talked about them in schools. He made them symbol of human curiosity and ambition. And through Sagan, the pioneers entered the cultural imagination. Kids drew pictures of spacecraft. They imagined what it would be like to ride on Pioneer 10. They thought about what it would mean to be that far from home, to be traveling into the void, carrying a message to the stars. The golden record became iconic. It still is. If you go online, you can find images of it. You can read about its contents. You can listen to samples of the music. It's become a symbol of humanity reaching out to the cosmos. The pioneers also influenced how we think about the long-term future. Before the pioneers, space exploration seemed like something that happened in brief, dramatic moments. A launch, a landing, a triumphant return. But the pioneers showed that space exploration could be something else. It could be a journey, a quest, something that took decades, something that outlasted the people who started it. This changed how we conceptualize the future. It made us think in longer timescales. It made us consider what we might create that would outlive us. And it made us think about legacy. What Pioneer 10 carries? Let me describe the golden record to you in more detail because I think it's important to really understand what we sent out there. It's a 12-inch phonograph record, like a vinyl record, gold-plated, encased in a protective aluminum cover. On the cover is a diagram showing how to play the record. It's drawn in a universal language. No words, just symbols. Inside the record are 115 images, photographs of Earth, of people, of landscapes, of cities and nature and human activity. There are images of mathematical and physical diagrams, images meant to convey scientific information. The images were chosen to represent the diversity of human experience. There are photographs of different races of people, different cultures, different landscapes from around the world. The intention was to show that Earth is inhabited by many different kinds of humans, many different ways of living. There are 90 minutes of music, not just Western classical music. There's music from around the world, Indian ragas, Peruvian panpipes, Japanese shakuhachi, Georgian choral music, and yes, there's Johnny B. Good. There are greetings, messages from world leaders, but also messages from ordinary people, school children, scientists, artists, people from different countries saying hello in their own languages. There are natural sounds, a mother and child talking, footsteps, heartbeat, laughter, ocean waves, wind, rain, thunder, whale songs, chimpanzees, crickets, frogs, a dog barking. There's a message from UN Secretary General Kurt Wollheim. There's also a message from Carl Sagan and his colleagues explaining what the record is. And there's a map, a star map showing the position of our solar system relative to the nearest pulsars. Pulsars are neutron stars that emit regular pulses of radiation. They're like cosmic lighthouses. And they're unique. Each pulsar has its own signature frequency. The idea is that if an alien civilization finds this record, they can use the pulsar map to triangulate our location. They can figure out where we came from. This is, in a sense, giving them our address in the cosmos. Now think about all of this. Think about what it means that we made these choices. We chose to include images of nude people. In some cultures, this was controversial. Some people thought it was inappropriate, but the decision makers felt it was important to show the human body, to show what we actually look like. We chose to include rock and roll music, which some felt was too American, too frivolous. We chose to include whale songs, which represent a different kind of intelligence, a different kind of consciousness. We were saying, on Earth, we're not the only intelligent species. There are others. We chose to include the sound of a human heartbeat, which is as fundamental as it gets. It's the sound of life. Every single choice on that record was deliberate. It was a conversation among scientists and artists about what it means to be human, what's essential about our civilization, what we want the universe to know about us. And then we sent it into the void, the philosophical weight. Here's what I keep coming back to. and I think it's important. The pioneers carry philosophical weight. They're not just machines, they're statements. They're arguments about what matters, about what's worth preserving, about what we want to say about ourselves. When you decide to include Chuck Berry's Johnny B. Good on a golden record being sent into space, you're making a statement. You're saying, this is important, this is human, this is worth preserving. When you include mathematical diagrams and scientific formulas, you're saying, we understand the universe. We've created a systematic body of knowledge. We think in abstract terms. We use mathematics to describe reality. When you include whale songs, you're saying, we recognize intelligence in other species. We value other forms of consciousness. We're not the only things that matter on our planet. When you include the voices of children, you're saying the future matters. The next generation matters. There's hope. All of these statements are encoded in the golden record. They're traveling on Pioneer 10 right now. They're billions of miles away from Earth, but they're still carrying these messages. Carl Sagan understood this. He knew that the pioneers weren't just about exploring space. They were about exploring what it means to be human. In his book, Murmurs of Earth, which is about the creation of the Voyager Golden Record, a similar but updated version, Sagan wrote about the process of deciding what to include. He talked about the philosophical questions it raised. What is essential about human civilization? What would we want aliens to know? What would we want to preserve if we could only send a few images and a little bit of music? These are the kinds of questions that the pioneers force us to ask. And the answers we came up with say something profound about who we are, about what we value, about what we think matters. The loneliness. But here's the other side of it. The pioneers also carry a sense of profound loneliness. We built these machines and sent them out knowing they would probably never fulfill their stated purpose, knowing that probably no alien civilization would ever find the golden record, knowing that this message we so carefully crafted would probably just drift in space forever unheard. And we did it anyway. There's something deeply melancholic about that. It's like writing a letter and putting it in a bottle and throwing it into the ocean, knowing almost certainly that nobody will ever find it. But writing it anyway, because you have to, because you need to reach out, because the act of reaching out is itself important, even if it's almost certainly futile. The pioneers embody this melancholy. They're beautiful and hopeful and philosophical, but they're also symbols of humanity's loneliness in the cosmos. We're alone here. As far as we know, Earth is the only place in the universe where life exists. We've looked and looked for signs of other intelligent civilizations, and we haven't found anything. The universe appears to be empty, and yet we keep reaching out. We keep sending messages. We keep hoping. The pioneers are an expression of that hope, and also an expression of that loneliness. The scientific legacy, let's talk about what the pioneers actually discovered, because while I've been focusing on the philosophical and cultural aspects, they also did real science. Important science. Pioneer 10's measurements of Jupiter's magnetosphere fundamentally changed how we understood planetary magnetic fields. We learned that Jupiter's magnetosphere was far more complex and dangerous than we'd expected. We learned about radiation belts that could harm electronic equipment. This information was crucial for designing future spacecraft. We learned what would and wouldn't work near giant planets. We learned how to shield electronics from radiation. Pioneer 11's measurements of Saturn provided our first detailed look at the Saturnian system, the rings, the moons, the magnetic field. This information formed the basis for all our future missions to Saturn. When Cassini went to Saturn in 1997, it was building on the foundation that Pioneer 11 had laid. Both Pioneers measured the solar wind, the streams of charged particles flowing out from the sun. They measured cosmic rays, the high-energy particles coming from beyond the solar system. They measured the interplanetary magnetic field. All of this data contributed to our understanding of the heliosphere, the bubble of space influenced by the sun. We learned that this bubble extended farther than we thought. We learned about its structure and composition. The pioneers also proved that we could navigate spacecraft using gravity assists, that we could use the gravity of planets to change a spacecraft's trajectory without using fuel. This technique would become standard for all future missions. And the pioneers proved that spacecraft could be built to last decades, that their instruments would continue functioning, that we could maintain communication across billions of miles. All of this seems obvious now. We take it for granted, but it wasn't obvious then. The pioneers had to prove it. The perspective shift. There's something else the pioneers did that I think is really important. They changed how we see our place in the universe. Before the pioneers, our exploration of space was limited to our immediate neighborhood. We went to the moon, which is next door. We orbited Earth. We sent probes to Venus and Mars. But we hadn't really left the solar system. We hadn't taken that step. The pioneers changed that. Pioneer 10 crossed an invisible but important boundary. It passed the orbit of Neptune. It went beyond the region where the planets are. It entered the realm of the truly deep space. And from that perspective, Earth looks different. The pioneers sent back pictures of Earth taken from millions of miles away. They showed us what our planet looks like when you're far enough away. It's small. It's fragile. It's blue and white and beautiful and unique. Carl Sagan talked about this. He talked about how seeing Earth from space, seeing it as a small, isolated world in an infinite cosmos, changes your perspective. It makes you realize how precious it is, how unique. There's a term for this, the overview effect. It's the cognitive shift that astronauts experience when they see Earth from space. They realize how small and interconnected everything is, how artificial the national borders are, how fragile the atmosphere is. The pioneers gave all of us a version of this. They showed us our world from far away, and it changed something in us. After the pioneers, we started to think differently about Earth. We started to care more about the environment. We started to understand that Earth is a single system, that all of us, all of humanity, are in this together. The first Earth Day was in 1970, 2 years before Pioneer 10 launched. But by the time the pioneers were sending back their data in the 1970s and 1980s, environmentalism was becoming a major force in culture. I don't think that's a coincidence. I think the pioneers and the perspective shift they enabled contributed to that change. The engineering philosophy. Let me talk for a moment about the people who built the pioneers, because their approach to engineering teaches us something. The pioneers were built to be simple. Not simplistic, simple. There's a difference. Simple means only include what you need. Don't add extra stuff. Make every component count. Make every system reliable. This was born out of necessity. The budget was limited. The payload capacity was limited. So you had to be ruthless about what you included. But this limitation forced innovation. The engineers had to think creatively about how to accomplish their goals with minimal resources. This is a principle that would influence spacecraft design for decades to come. The idea that constraints breed innovation, that sometimes having less forces you to be smarter. The pioneers also embodied a philosophy of redundancy, where possible critical systems were backed up. If one communication antenna failed, there was another. If one solar panel failed, though the pioneers didn't use solar panels, but other spacecraft did, there were others. This wasn't about being safe, it was about maximizing the chances of mission success. And it worked. The pioneers lasted far longer than anyone expected, partly because they were built robustly, because the engineers had thought about what could go wrong and had built in protections. There's a lesson here about engineering philosophy. It's not about making things complicated, it's about making things that work, that survive, that can handle unexpected challenges. The pioneers were masterpieces of this philosophy. The data that keeps giving. Here's something fascinating. Scientists are still analyzing data from the pioneers. Decades after the spacecraft went silent, researchers are still looking at the data they sent back. They're still discovering new things. Why? Because the pioneers measured regions of space that we couldn't measure any other way. They went places no other spacecraft had gone. They took measurements that nothing else had taken, and sometimes you don't fully understand what you've measured until years or decades later. A good example is the Pioneer anomaly one mentioned earlier. It took decades of analysis to figure out what was causing the trajectory deviation. But by solving it, scientists learned things about thermal radiation and spacecraft physics that might not have been discovered otherwise. Similarly, the Pioneer's measurements of cosmic rays have been analyzed and reanalyzed over the years. Scientists use them to understand the structure of the heliosphere, to understand how particles move through space, to understand the boundary between our solar system and interstellar space. The Voyagers, which came after the Pioneers, have also been an incredible source of long-term data. Voyager 1 is still transmitting. It's still sending back measurements from interstellar space. And those measurements are revealing things we never expected. There's a lesson here about the value of long-term observation. You can't always understand what you're measuring in real time. Sometimes you need decades of reflection, decades of analysis, decades of having the data available for new researchers to look at with fresh perspectives. The pioneers proved this. They proved that spacecraft sent out to explore can continue to be valuable long after their original mission objectives are complete. The stories they tell. I want to shift gears for a moment and talk about the narrative of the pioneers. Because there is a narrative here. There's a story. The story begins with ambition, with humans looking at the solar system and saying, we want to go there. We want to explore. We want to know. It continues with engineering, with brilliant people solving impossible problems, with constraints that force creativity. Then comes the launch, the moment when the dream becomes real, when the machine leaves the Earth and starts its journey. Then comes the exploration, the encounters with planets, the discoveries, the moment of flying by Jupiter or Saturn and learning something new about the universe. And then comes the long journey, the decades of travel through empty space, the gradual fading, the silence. And finally, and this is important, comes the legacy, the way the pioneers changed how we think, the way they influenced future missions, the way they continue to teach us things. This is a complete narrative arc. It has a beginning and a middle and an end. It has drama and wonder and melancholy. And it's a deeply human story because it's about us, about what we're capable of, about our desire to explore, about our willingness to send things away, knowing we might never hear from them again. The pioneers tell a story about humanity, about who we are, about what we value, and that story is worth telling. It's worth remembering. The moment of connection. I want to talk about something that happened on September 5th, 2013. That was the day that Voyager 1, the successor to Pioneer 10, officially left the solar system and entered interstellar space. Scientists at NASA announced it. They confirmed that Voyager 1 had crossed the heliopause. It was now traveling through space that had never been reached by any human-made object before. And you know what happened? The internet exploded. People cared. People paid attention. Years after Voyager 1 had launched in 1977, people were still moved by this achievement, still fascinated by the idea of a human spacecraft reaching interstellar space. Why? I think it's because of what the pioneers had done. The pioneers had made space exploration cool again. They had made the long journey seem important. They had shown that exploration wasn't just about the dramatic moment, it was about the persistence, the journey, the slow, patient push into the unknown. The Voyagers benefited from this cultural shift. And when Voyager 1 reached interstellar space, people understood why it mattered. They understood the significance. This is the legacy of the pioneers. They didn't just explore space. They changed how we think about space. They made us understand that the long journey is important. That exploration doesn't have to be quick and dramatic. It can be slow and patient and meaningful. The signals we send. Let me return to the golden record for a moment, because I think there's something profound about the act of creating that record, about deciding what to include, about crafting a message to send out into the void. It's an act of hope. It's saying, maybe someone out there will hear this. Maybe someone out there will know we existed. Maybe someone out there will care that we were here. And even if nobody ever hears it, we needed to do it. We needed to reach out. We needed to say something. This impulse, this need to reach out, to communicate, to say something to the universe, it's deeply human. We write letters. We make art. We create music. We do all of these things partly because we hope someone will appreciate them, but also partly because the act of creating them matters, regardless of whether anyone appreciates them. The pioneers were like that. They carried a message that probably will never be received. But we sent it anyway, because we needed to. Carl Sagan understood this. In his writings about the Voyager record, he talked about how the act of creating it was meaningful, even if it never served its intended purpose. He said something like, even if no alien civilization ever finds this, we have made a statement about ourselves. We have created something beautiful. We have reached out into the cosmos. And that matters. The philosophy of leaving. Here's something that I find really interesting. The pioneers represent humanity's first real decision to leave something behind. We sent people to the moon, and they came back. We sent spacecraft to other planets, and some of them came back. At least the sample returns did. But with the pioneers, we sent something that we knew would never come back. Something that would drift in space forever. Something that was a one-way trip. This is philosophically important. It's a shift from exploration that's about returning with discoveries to exploration that's about the journey itself, about sending something out and accepting that we won't get it back. In some cultures and religions, this has deep significance. There's the idea of sacrifice, of giving something away, of letting go. The pioneers were, in a sense, a sacrifice. We built them carefully. We loaded them with our best technology. We gave them our messages and our music, and then we let them go. We accepted that we would lose them. This is different from previous space missions. It's a more mature understanding of exploration. It's accepting that some things we create are meant to leave us. And there's something beautiful about that. There's something that speaks to a deeper understanding of the human condition. We are creatures who create, who build things. And part of the deal is that sometimes the things we create are meant to leave us, are meant to become independent of us. The pioneers teach us this lesson. The present day. So where are we now in 2026? Pioneer 10 has been in space for over 50 years. Its last signal was in 2003. We don't know if it still exists, but we assume it does. We assume it's still traveling, still carrying its golden record out into the void. Pioneer 11's last signal was in 1995. We haven't heard from it in over 30 years. But Voyager 1 is still transmitting. As of 2026, it's still sending data back to Earth from interstellar space. It's the most distant spacecraft humanity has ever built. It's over 24 billion kilometers from Earth. It's been in space for nearly 50 years. And it's still alive, still reaching back to tell us about the universe. The Voyagers are the successors to the pioneers. They're bigger, more sophisticated, better equipped, but they exist because the pioneers proved it was possible. And the Voyagers carry their own golden records, updated versions, with more music, more images, more messages. In 2027, Voyager 1 will be 50 years old. On its 50th anniversary, NASA will likely do something to commemorate it. There will be press releases, there will be articles. People will remember this incredible spacecraft that's still working, still transmitting after 5 decades in space. And people will think about the pioneers, because the pioneers came first. Because without them, there would be no Voyagers. This is how legacy works. The pioneers are gone. We can't hear them anymore. But their influence remains. Their influence is still felt in every spacecraft we send beyond Earth's immediate vicinity. What we left behind. Let me think about this from a different angle. What if aliens did find Pioneer 10? What if 10,000 years from now, an alien civilization in some distant star system encountered our spacecraft? What would they learn about us? They would learn that we made music, that we valued beauty and art, that we sent Chuck Berry and Mozart and Indian ragas into space because we thought music was important. They would learn that we were curious, that we wanted to explore, that we had the capability to build machines that could travel between stars. They would learn that we were diverse, that we had many cultures, many languages, many ways of living. They would learn that we valued other forms of life, that we included whale songs on our record because we recognized intelligence in other species. They would learn that we were hopeful, that we believed in the future, that we thought it was possible to solve our problems and join a community of galactic civilizations. They would learn that we were alone. At least we seem to be. Because the record comes from a single planet, a single world, the only world we knew to have life on it. They would learn that we were fragile, that we lived on a thin shell of rock surrounded by a thin atmosphere, that if something went wrong, we would have nowhere else to go. And they would learn that despite all of this, despite being alone, despite being fragile, despite our limitations, we reached out. We created something. We sent it into the void. We said, here's what we are. Here's what we think. Here's what we value. If that's not a profound statement about humanity, I don't know what is. The ongoing mission. Here's something I want to emphasize. The missions of the Pioneer spacecraft never really ended. They're still ongoing. Even though we can't hear from them anymore, they're still transmitting. Somewhere in the void, Pioneer 10 and Pioneer 11 are still moving, still traveling, still carrying their messages. The mission isn't over just because we stopped receiving signals. The mission continues as long as the spacecraft continues to exist. And scientists estimate that Pioneer 10 could continue existing, could continue traveling through space for millions of years, maybe longer. In that sense, the Pioneer mission is one of the longest duration projects humanity has ever undertaken. It started in 1972. It will continue for millions of years into the future, billions of years potentially. Eventually, Pioneer 10 will leave our galaxy. It will travel to another galaxy, and then another, and eventually so far in the future that we can't even conceive of it, it might encounter something. Or it might not. But it will keep traveling. It will keep carrying humanity's message. This is a kind of immortality. Not the biological kind, but the kind where something you created continues to exist long after you're gone, continues to travel, continues to represent you. The pioneers are humanity's immortals. They're the part of us that we sent out to live forever in the cosmos. I want to end by talking about what the pioneers mean to me and what I think they should mean to all of us. The pioneers are a statement about human nature. They say, we are creatures who explore, who reach out, who create things and let them go into the unknown. They say, we value beauty and art and music. We think these things are important enough to send into space. They say, we are alone, but we reach out anyway. We send messages that probably will never be received. We create golden records that probably will never be played. We do it anyway because we have to, because it's important. They say, we believe in the future. We believe in the possibility of contact. We believe that someday, somehow, our messages might matter. The pioneers are hopeful, but they're also melancholic. They're beautiful, but they're also sad. They're the most human thing we've ever created in a way, because they embody both our highest aspirations and our deepest loneliness. Carl Sagan used to say that we're a way for the cosmos to know itself, that the universe created consciousness so that it could observe itself, so that it could wonder about itself. The pioneers are an expression of that. They're the universe wondering about itself. They're humanity reaching out and saying, we are here, we think, we feel, we create. And if that's all the pioneers ever do, if they never make contact with anyone, if they drift forever in the void unheard, it's enough. Because the act of reaching out is itself meaningful. The act of saying something to the cosmos, even if no one ever hears it, matters. The pioneers proved that. And for that, I think we should be grateful. There's one more thing I want to say. In a world that often feels overwhelming, in a time when we're dealing with climate change and political division and inequality and all the weight of human problems, it's easy to forget that we're capable of doing things like building the pioneers, creating golden records, sending messages to the stars. It's easy to feel small and powerless, but the pioneers remind us that we're not, that humanity is capable of extraordinary things, that we can build machines that last for decades, that we can reach beyond our world, that we can create beauty and meaning even in the face of an uncaring universe. The pioneers are a reminder of what we're capable of, and in a time when we need reminders, that matters. So the next time you think about space, the next time you look up at the night sky, remember the pioneers. Remember that out there, somewhere beyond the edge of the solar system, there are two golden machines traveling through the void. They're carrying our messages, our music, our images, our hope. They're the longest duration missions humanity has ever undertaken. They're proof that we can reach out, that we can explore, that we can create something that will outlive us. And they're beautiful. The pioneers are beautiful. And as long as they're out there traveling through space, carrying humanity's messages to the stars, there's a part of us out there too. There's a part of us that's reached beyond our world. That's touched something vast and eternal. That said, we are here. We existed. We mattered. And that, I think, is enough. That's more than enough. Let me take a step back and really appreciate the engineering achievement of the pioneers from a technical standpoint. Pioneer 10 weighed about 260 kilograms. That's roughly the weight of a grown man. A machine the size of a small car, built to travel billions of miles from Earth, to survive in radiation environments we didn't fully understand, to maintain its systems and continue communicating across incomprehensible distances. The spacecraft was powered by radioisotope thermoelectric generators, RTGs. These devices contain plutonium-238, a radioactive isotope. As the plutonium decays, it releases heat. That heat is converted into electricity by thermocouples. This is brilliant because it doesn't require sunlight. Unlike solar panels, RTGs work just as well in the dim light of the outer solar system as they do near Earth. In fact, they work better far from the sun. The heat differential between the hot side, warmed by the radioactive decay, and the cold side, exposed to the cold of space, is greater when you're far from the sun's warmth. The downside is that the fuel decays. Over time, as the plutonium breaks down, the power output decreases. Pioneer 10 launched with about 150 watts of power. By the time it reached Jupiter, that had dropped to about 130 watts. By the time it reached the edge of the solar system, it was down to less than 10 watts. 10 watts. Think about that. A typical household light bulb uses 60 watts. Pioneer 10 was operating on less than 1/6 the power of a light bulb, while trying to transmit data across billions of miles and maintain all its scientific instruments. The engineers had to design every system to be incredibly efficient. Every component had to do more with less. The computers aboard Pioneer 10 were primitive by modern standards, far less powerful than a modern smartphone, but they were sophisticated enough to control the spacecraft, manage the instruments, and maintain the radio communication. The radio system itself was a marvel. It transmitted at a power of only about 10 watts. That's the same power as a nightlight. And yet this signal had to travel billions of miles through the vacuum of space, through interference and radiation, and still be detected by antennas on Earth. When Pioneer 10 was at its farthest, its signal had to travel for over 11 hours to reach Earth. By the time it arrived, it had been attenuated to a signal so faint that it amounted to just a few photons per second. The antennas of the Deep Space Network had to be incredibly sensitive to detect it, but they did. For decades they did. The trajectory and navigation. Let me talk about how the pioneers were navigated. Both Pioneer 10 and Pioneer 11 were navigated using what's called a gravity assist trajectory, or a Hohmann transfer orbit with gravity assists. The basic idea is this. Instead of flying directly to Jupiter, you use Earth's gravity to give yourself an initial boost. Then you let the spacecraft coast through interplanetary space. Then, when you reach Jupiter, you use Jupiter's gravity to change your trajectory and send yourself deeper into the solar system. This is incredibly efficient from a fuel perspective. It uses the gravity of planets to redirect the spacecraft without burning additional fuel. But it requires precise calculations. You have to know exactly where Jupiter will be when your spacecraft arrives. You have to calculate the exact trajectory that will bring your spacecraft close enough to Jupiter for the gravity assist to work, but not so close that you crash into the planet. The engineers who calculated these trajectories were using computers far less powerful than what we have now. They had to do complex calculations by hand, checking their work multiple times, and they got it right. Both Pioneer 10 and Pioneer 11 followed their planned trajectories with remarkable accuracy. After passing Jupiter, or Saturn, both spacecraft were essentially on autopilot. They had no way to correct their course. They had no ability to change direction. Once they left the inner solar system, their trajectory was essentially fixed, and yet they continued to transmit. They continued to maintain their orientation. They continued to function. This speaks to the robustness of their design. The engineers had built in enough redundancy, enough reliability, that the spacecraft could maintain themselves for decades without any ability to make corrections. The challenges of communication. Let me talk about the challenges of communicating with distant spacecraft. As a spacecraft gets farther from Earth, the signal strength decreases. This is just physics, the inverse square law. If you double the distance, the signal strength drops to 1/4. If you triple the distance, it drops to 1/9. By the time Pioneer 10 was at the edge of the solar system, it was about 4.6 billion miles from Earth. That's more than 30 times farther from Earth than Earth is from the Sun. At that distance, the signal strength had dropped enormously. The antennas had to be incredibly sensitive. The signal had to be incredibly precisely encoded. And there's another problem, the Doppler shift. When a source of waves, sound, light, radio waves, is moving toward you, the waves get compressed. The frequency increases. When it's moving away from you, the waves get stretched out. The frequency decreases. Pioneer 10 was moving away from Earth. Its radio signal was being Doppler shifted to a lower frequency. The engineers had to account for this shift when trying to decode the signal. But there's more. The signal was also being affected by the solar wind, the stream of particles coming from the sun. As the signal passed through this plasma, it was being scattered and refracted. The signal was also being bent by the gravity of the sun. Yes, gravity affects electromagnetic waves too. The sun's gravity was slightly bending the path of Pioneer's radio signal. All of these effects had to be accounted for. The engineers had to predict what the signal would look like when it arrived at Earth, and then build receivers that could detect it despite all these distortions. It's an incredible feat of engineering and physics. The data rate problem. Here's another challenge, the data rate. As Pioneer 10 got farther from Earth, not only did the signal get weaker, but the amount of data that could be transmitted decreased. The radio system could only transmit so much information per unit time. This is limited by the laws of physics. The weaker the signal, the less information you can encode in it. In the early days when Pioneer was near Jupiter, it could transmit data at a rate of about 1024 bits per second. That's about 128 bytes per second. By modern standards, that's incredibly slow. A modern broadband internet connection transmits millions of bits per second. But for Pioneer, Transmitting data from Jupiter was already pushing the limits of what was possible. By the time Pioneer reached the outer solar system, the data rate had dropped to just a few bits per second. A few bits per second. That's how much information could be transmitted across billions of miles. The engineers had to decide what information is most important. What do we want to know about the spacecraft's status and the space it's traveling through? They prioritized. They sent the most critical information: the spacecraft's orientation, its power status, temperature readings, and data from the scientific instruments, the measurements of the solar wind, the cosmic rays, the magnetic fields. Everything else was sacrificed. You couldn't transmit high-resolution images. You couldn't transmit detailed readings from every sensor. You had to choose. This constraint shaped how the mission was designed. It shaped what scientific questions could be answered. It's a good example of how practical constraints influence how we explore space. The cosmic ray measurements. I want to talk more about what the pioneers actually measured because it's fascinating. One of the primary instruments on Pioneer was a cosmic ray detector. This instrument could detect high-energy particles coming from beyond the solar system. These particles, mostly protons, but also heavier nuclei, are some of the most energetic things in the universe. They're created by exploding stars, by black holes, by other cataclysmic cosmic events. They travel through space at close to the speed of light. And occasionally, one of them hits Earth's atmosphere. But the solar wind, the stream of charged particles coming from the sun, acts as a shield. The sun's magnetic field, carried by the solar wind, can deflect some of these cosmic rays, preventing them from reaching the inner solar system. The pioneers measured the cosmic ray flux at different distances from the sun. They found that it increased as they moved away from the sun. This confirmed that the sun's magnetic field was indeed shielding the inner solar system from cosmic rays. But the pioneers also discovered something unexpected. There were variations in the cosmic ray flux. Sometimes it would increase, sometimes it would decrease. These variations seem to be correlated with activity on the sun. Solar flares, sudden bursts of activity on the sun's surface, would sometimes cause the cosmic ray flux to decrease. This was a new discovery. It showed that the sun's activity had effects that could be measured billions of miles away. This data from the pioneers formed the basis for our modern understanding of cosmic ray modulation, how the sun influences the cosmic rays that reach the inner solar system. And we still don't fully understand it. Scientists are still analyzing Pioneer data, trying to understand the mechanisms behind these variations. The magnetosphere discoveries Pioneer 10's encounter with Jupiter revealed something shocking. Jupiter has a massive magnetosphere. A magnetosphere is a region of space around a planet where the planet's magnetic field dominates. Earth has a magnetosphere, but it's relatively small and weak compared to Jupiter's. Jupiter's magnetosphere extends millions of kilometers into space. It's one of the largest structures in the solar system. If you could see it, it would appear much larger than the Sun to someone standing on Jupiter. Pioneer 10 measured this magnetosphere. It found that it was far more complex than anyone expected. There were radiation belts, regions where charged particles were trapped by Jupiter's magnetic field and accelerated to high energies. These radiation belts were intense. Pioneer 10 had to be shielded to protect its electronics from the radiation. But even with shielding, the spacecraft was exposed to radiation levels that would have been harmful to any human aboard. This was important for future missions. When we sent astronauts to the moon, we had to make sure they wouldn't be exposed to dangerous radiation from Earth's magnetosphere. The data from Pioneer about Jupiter's magnetosphere helped us understand how dangerous magnetospheres could be. Pioneer 11 made similar discoveries at Saturn, though Saturn's magnetosphere is weaker than Jupiter's. These discoveries about planetary magnetospheres shaped how we designed spacecraft that would later visit these planets. We had to account for the radiation. We had to shield our instruments. We had to accept that exploring giant planets was inherently dangerous, even for robots. The solar wind measurements. Another key measurement the pioneers made was of the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing out from the sun at high speed. It's typically moving at around 400 kilometers per second. The solar wind has a pressure. It pushes on everything it encounters. In the inner solar system, this pressure is significant. It affects the tails of comets, pushing them away from the sun. It affects the magnetospheres of planets. The pioneers measured the solar wind speed, density, and direction at different distances from the sun. They found that the solar wind properties changed with distance. The density decreased. The speed remained relatively constant. This data was used to construct models of the solar wind. Understanding the solar wind is important for understanding the heliosphere, the bubble of space around the sun that's filled with the solar wind. The heliosphere is bounded by the heliopause, the boundary where the solar wind's pressure equals the pressure of the interstellar medium beyond. For decades, scientists weren't sure exactly where the heliopause was. Was it at the orbit of Neptune, beyond the Kuiper belt? Further, the Pioneer data helped constrain this question. The Pioneers showed that the solar wind extended farther than anyone expected. Eventually, the Voyager spacecraft would confirm that the heliopause is about 120 astronomical units from the Sun. That's far beyond the orbit of Neptune. Voyager 1 crossed it in 2012, but the Pioneers provided the first hints that it was that far out. The interplanetary magnetic field. The Pioneers also measured the interplanetary magnetic field, the Sun's magnetic field carried by the solar wind into space. This field is weak, but it's not zero. It has a structure. It's shaped like a spiral, rotating with the sun. Imagine the sun spinning. As it spins, it drags its magnetic field with it. The solar wind carries this magnetic field outward, but because the sun is rotating, the field is twisted into a spiral shape. The Pioneers measured this field at different distances. They confirmed the spiral structure. They measured its strength and direction. This data was important for understanding the large-scale structure of the heliosphere. It's important for understanding how cosmic rays are modulated. It's important for understanding solar wind dynamics. Again, this is the kind of foundational data that forms the basis for decades of future research. The Pioneers provided measurements that scientists are still using to understand the solar system. The asteroid belt crossing. Let me talk about one specific moment in Pioneer 10's journey: crossing the asteroid belt. Before Pioneer 10, there was concern about whether a spacecraft could even survive crossing the asteroid belt. The asteroid belt is a region of space between Mars and Jupiter filled with thousands of rocky bodies. Scientists worried, would the spacecraft hit an asteroid? Would the density of asteroids be too high to safely cross? This turned out to be unfounded. The asteroid belt is actually quite sparse. The asteroids are spread out over a huge volume of space. The chances of hitting one are incredibly small. Pioneer 10 crossed the asteroid belt without incident. It didn't hit a single asteroid. This was important because it showed that it was safe to send spacecraft to the outer planets. You didn't have to worry about asteroid collisions. The belt was navigable. This finding influenced all future space exploration. Every subsequent spacecraft that went to Jupiter, Saturn, Uranus, or Neptune crossed the asteroid belt successfully. None of them hit anything. We now send spacecraft through the asteroid belt routinely. We've even landed spacecraft on asteroids. We've sent probes through the belt so many times that we know with confidence that it's safe. But Pioneer 10 was the first. It was the spacecraft that proved it could be done. The encounter with Jupiter. The moment when Pioneer 10 flew by, Jupiter was extraordinary. December 3rd, 1973. Pioneer 10 passed closest to Jupiter at a distance of about 130,000 kilometers. That's about 1/3 of the distance from Earth to the Moon. At that moment, Pioneer 10 was traveling at incredibly high speed. The gravity of Jupiter had accelerated it. It was moving at tens of kilometers per second relative to Jupiter, and the spacecraft's instruments were working perfectly. The cameras were taking pictures. The spectrometers were analyzing the light from Jupiter. The radiation detectors were measuring the intense radiation. For the first time, humans saw Jupiter up close, not just as a bright dot in the sky, but as a real world. A giant planet with storms and bands of cloud, with moons and a magnetosphere. The data and pictures that Pioneer 10 sent back transformed our understanding of Jupiter. We learned about the Great Red Spot, a storm larger than Earth that has been raging for at least 300 years. We learned about Jupiter's rings. Yes, Jupiter has rings. They're not as dramatic as Saturn's, but they're there. Pioneer 10 discovered them. We learned about Jupiter's intense radiation belts. We measured the radiation levels and confirmed that they were much higher than anyone had expected. We got our first close-up views of Jupiter's large moons, Io, Europa, Ganymede, and Callisto. Io turned out to be volcanically active. There were volcanoes erupting on its surface. This was the first discovery of active volcanoes beyond Earth. Europa was revealed to have a smooth, icy surface, crisscrossed with cracks. Scientists immediately speculated, could there be liquid water under that ice? Could there be life? These questions would drive planetary science for decades. Decades later, the Galileo spacecraft would confirm that Europa probably does have a subsurface ocean. Future missions are being planned to go back and search for life there. But it all started with Pioneer 10, with that first close encounter, with that first transmission of data back to Earth. The moment of greatest discovery. There's something poignant about thinking about the moment when Pioneer 10 made its closest approach to Jupiter. At that moment, the spacecraft was closest to Jupiter and farthest from Earth. The signal it was sending took nearly an hour to reach Earth. So when mission controllers on Earth saw the data from closest approach, it was already an hour in the past. But they understood what they were seeing. They understood that Pioneer 10 had done what no spacecraft had done before. It had reached another planet. It had measured it. It had sent back data and images. And then it kept going. It passed Jupiter and continued outward. It was leaving the sun's immediate neighborhood and heading into the deep solar system. This was the beginning of the real journey. The encounter with Jupiter was spectacular, but it was just one moment. The real mission was what came after. The long, slow journey to the edge of the solar system. Pioneer 11's journey. Let me talk about Pioneer 11 because it had a different trajectory and discovered different things. Pioneer 11 was launched a year after Pioneer 10. It followed a different path through the solar system. Instead of going directly to Jupiter, it took a slightly different trajectory. Then, at Jupiter, Instead of continuing outward like Pioneer 10, Pioneer 11 was aimed at Saturn. Flying by Jupiter gave Pioneer 11 the gravity assist it needed to reach Saturn. And on September 1st, 1979, Pioneer 11 flew past Saturn. This was the first spacecraft to reach Saturn. The data it sent back was extraordinary. We got our first close-up views of Saturn's rings. We confirmed they were made of ice and rock. We measured their structure. We discovered new rings that hadn't been visible from Earth. We got our first close-up views of Saturn's largest moon, Titan. We saw that it had a thick atmosphere, the only moon in the solar system with a substantial atmosphere. We measured Saturn's magnetosphere. We found that it was smaller and weaker than Jupiter's, but still significant. We got our first images of Saturn's smaller moons. We discovered new moons that hadn't been known before. And then Pioneer 11 continued outward, like Pioneer 10 before it. It left Saturn and headed into the deep solar system. Both Pioneers were now heading outward, toward the edge of the solar system, toward interstellar space. The long silence. At some point, the signals from the Pioneers began to fade. This wasn't because the spacecraft were broken. It was because they were getting farther away, and their power was decreasing as the radioactive fuel decayed. Eventually, the signals became so weak that even the most sensitive antennas on Earth could barely detect them. Mission controllers had to decide, when do we stop trying to listen? When do we accept that we can no longer communicate with these spacecraft? For Pioneer 10, the last signal was received on January 23, 2003. That was 30 years after launch. 30 years of continuous communication. By that point, Pioneer 10 was over 12 billion kilometers from Earth. It was in a region of space that humans had never reached. It was the farthest spacecraft humans had ever built. For Pioneer 11, the last signal came earlier, in November 1995, after about 18 years of communication. When the last signals were received, there was a sense of closure, but also a sense of loss. These spacecraft had been humanity's ambassadors to the outer solar system. They had been our eyes and our ears beyond the planets. And now they were gone, but not really gone. They were still out there, still traveling, still carrying their instruments and their golden records. Just silent. The Pioneer Anomaly Revisited. I mentioned the Pioneer Anomaly earlier, but I want to explore it in more depth because it's a fascinating scientific mystery. Starting in the late 1970s, engineers and scientists noticed something odd. The Pioneer's trajectories didn't match predictions. The spacecraft were being pulled back toward the sun slightly more strongly than general relativity and classical mechanics predicted. There was an anomalous acceleration, an extra deceleration of about 8.74 times 10 to the minus 10 meters per second squared. This was tiny, incredibly tiny, but over decades it would accumulate. Over 30 years, this small acceleration would add up to a velocity change of nearly 100 meters per second. Scientists were puzzled. What could cause this? Some people speculated, could it be a sign of undiscovered physics? Could it be evidence of new forces or new particles? Others suggested more mundane explanations, measurement errors, unmodeled forces, or something about the spacecraft itself. The mystery persisted for years. Scientists analyzed the trajectory data from both Pioneers. They looked for any possible source of error. They proposed increasingly exotic explanations. But then, in 2012, a paper was published that solved the mystery. The culprit: thermal radiation from the spacecraft itself. Here's what was happening. The pioneers were powered by radioactive decay. That decay generates heat. Some of that heat radiates out into space. And when objects radiate heat asymmetrically, it creates a force. This is called the Yarkovsky effect when applied to asteroids, or the Poynting-Robertson effect when applied to solar radiation. But in this case, it was thermal radiation from the spacecraft's own heat source. The spacecraft's antennae were pointing toward Earth. The back of the spacecraft, opposite the antenna, was radiating heat into space. And because the radiation was asymmetrical, more on the back than the front, it created a small force pushing the spacecraft forward, which is equivalent to a small deceleration when viewed from Earth's perspective. Once engineers accounted for this effect, the Pioneer trajectories matched predictions perfectly. It's a beautiful example of how even tiny, seemingly negligible effects can add up over time. And it's an example of how scientific mysteries can be solved through careful analysis and creative thinking. But here's what I find most interesting. It took 30+ years to solve. The anomaly wasn't discovered until decades after the spacecraft had been launched. It wasn't solved until decades after that. This shows that even with all our understanding of physics, space exploration can still reveal surprises, can still teach us new things, can still challenge us. The search for extraterrestrial life. The golden records carried messages about humanity, but they also carried a message about the search for extraterrestrial life. By including whale songs on the record, we were saying, we recognize that life takes many forms. We recognize intelligence in species other than ourselves. We wonder about life elsewhere. And indeed, the search for extraterrestrial life has been a major theme in space exploration since the pioneers. The pioneers themselves were not equipped to search for life, but they carried the idea. They carried the question. Later spacecraft, like the Viking landers on Mars, would search for microbial life. They didn't find anything definitive, but they expanded our understanding of what conditions life could survive in. The Voyagers carried the golden records to the outer planets, and both pioneers and Voyagers measured environments that might be habitable. Today, we're planning to send spacecraft to Europa and Enceladus, moons that might have subsurface oceans where life could exist. All of this traces back, in a sense, to the pioneers, to the idea that we should explore, that we should look for life, that the universe might contain wonders we haven't imagined. The impact on planetary science. The pioneers fundamentally shaped planetary science. Before the pioneers, our knowledge of the planets beyond Earth came from Earth-based telescopes and from a few simple space probes. After the pioneers, we had detailed measurements of the outer solar system. We had close-up pictures of Jupiter and Saturn. We had data about their magnetic fields, their atmospheres, their radiation belts. This data transformed planetary science. It created new fields of research. It raised new questions. The discovery of active volcanism on Io led to research into what powers volcanism on moons. It led to understanding the role of tidal heating, how the gravitational pull of one body can heat another. The discovery of Titan's thick atmosphere led to research into planetary atmospheres. What conditions allow a moon to retain an atmosphere? What chemical processes happen in these atmospheres? The measurements of Jupiter's and Saturn's magnetospheres led to research into how planetary magnetic fields are generated and how they interact with the solar wind. The cosmic ray and solar wind measurements contributed to our understanding of the heliosphere and how it evolves with solar activity. Decades later, When spacecraft like Galileo went to Jupiter and Cassini went to Saturn, they built on the foundation that the pioneers had laid. The scientists designing these missions had the pioneer data to guide them. They knew what to look for. They knew what instruments to include. The pioneers made modern planetary exploration possible. The legacy in engineering. The pioneers also left a legacy in spacecraft engineering. They proved that spacecraft could be built to last decades, that they could operate in harsh radiation environments, that they could maintain their systems over long periods with minimal power. They pioneered the use of gravity assists for efficient spacecraft trajectories. They pioneered the use of radioisotope thermoelectric generators for long-duration deep space missions. They pioneered the use of redundancy and fault tolerance in spacecraft design. All of these innovations have been used in subsequent spacecraft. All of our modern deep space probes, the Voyagers, the Galileo, the Cassini, the Juno, the New Horizons, they all use technologies and design philosophies pioneered by the pioneers. In a sense, every successful space mission since the pioneers owes something to them. Every spacecraft that's explored the outer solar system has built on the foundation they laid. The cultural impact beyond science. The pioneers had an impact that went far beyond science. They captured the imagination of the public. Here were these machines, built by humans, traveling to places no human had ever been, sending back pictures and data from alien worlds. For the first time, people could see Jupiter and Saturn up close, not as artists' renditions or telescope images, but as real photographs, as places. This had a profound effect on how people thought about the solar system. It made the planets real. It made space exploration real. The pioneers inspired a generation of scientists and engineers. Young people saw these achievements and thought, that's what I want to do. I want to explore space. I want to understand the universe. Many of the people who work in space exploration today were inspired by the pioneers, by the Voyagers, by the dream of exploring the cosmos. The pioneers also became cultural icons. They appeared in science fiction. They were referenced in popular media. They became symbols of human achievement and exploration. Carl Sagan, in particular, used the pioneers as a way to talk about humanity's place in the universe. In his books and his TV series, he would reference the pioneers. He would talk about what they meant, about what they revealed about who we are. The pioneers became more than just spacecraft. They became philosophical statements. They became expressions of human values. The role of radio astronomy. The successful communication with the pioneers depended on advances in radio astronomy and antenna technology. The Deep Space Network, the system of large radio antennas used to communicate with distant spacecraft, was developed specifically to enable missions like the pioneers. These antennas are enormous. The largest ones are about 70 meters in diameter. That's about the height of a 20-story building. They have to be incredibly sensitive to detect the faint signals from distant spacecraft. A single photon from Pioneer's radio transmitter arriving at an antenna on Earth would need to be detected among the background noise. The receivers used with these antennas are cryogenically cooled to near absolute zero. This reduces electronic noise and allows them to detect extremely faint signals. The signal processing equipment used to extract data from these faint signals is sophisticated. It has to account for Doppler shifts, propagation delays, interference, and other distortions. The development of this technology was driven by the space program, and the technology has had spin-offs. Radio astronomy techniques developed for tracking spacecraft have been used in astronomy. Antenna designs developed for the deep space network have been used for other purposes. The pioneers, in a sense, spurred the development of technology that has applications far beyond space exploration. The pioneers raise profound philosophical questions. One question: what does it mean to explore? For most of human history, exploration meant traveling somewhere and returning with knowledge. Columbus sailed to the New World and came back. Magellan's expedition circled the globe. Explorers would go somewhere, document it, and return home. The pioneers are different. They're explorers that never come home. They explore and keep going. They're one-way missions. This changes the nature of exploration. It means accepting loss. It means sending something out knowing you won't get it back. It also means changing our relationship with the explored. Instead of taking samples and returning home, we're leaving something behind. We're putting humanity's imprint on the cosmos itself. Another question: what is the purpose of exploration? In the age of exploration, the purpose was often practical: to find resources, to establish trade routes, to expand empires. The pioneers aren't exploring for practical reasons. They're not bringing back gold or spices. They're not establishing colonies. They're exploring to understand, to satisfy curiosity, to see what's there. This is exploration in its purest form. Exploration motivated by the desire to know, by wonder, by the human drive to understand the universe. A third question: what message do we send to the cosmos? The golden records carried messages about humanity, but what does it mean to send a message to the cosmos? It's an act of faith in a way. We're saying, maybe someone will receive this. Maybe someone out there will know we existed. But even if no one ever receives it, the act of sending the message matters. It says something about us. It says we believe our existence is significant. We believe our creations are worth preserving. We believe in the possibility of contact. The pioneers are a beautiful example of the scientific method in action. Scientists made predictions about what the solar system would be like. They predicted that it would be safe to cross the asteroid belt. They predicted the properties of Jupiter's magnetosphere based on Earth's magnetosphere scaled up. Then the pioneers went out and tested these predictions. And in many cases, the predictions turned out to be wrong, or only partially right. Jupiter's magnetosphere turned out to be far larger and more intense than expected. The asteroid belt turned out to be empty enough to safely cross, confirming predictions on that front. The solar wind turned out to extend much farther than expected. Science progresses through this cycle of prediction and observation. We make a prediction. We test it. If it's wrong, we revise our understanding. If it's right, we learn something new. The pioneers drove this cycle forward. They forced us to confront our assumptions. They revealed things we didn't expect to find. And this process continues. Decades after the pioneers stopped transmitting, scientists are still analyzing their data. New instruments and new analytical techniques reveal things in the data that weren't apparent before. A paper published in 2020 reanalyzed Pioneer 10's measurements of cosmic rays and found new insights into solar wind modulation. The pioneers keep teaching us. They keep pushing science forward. The passage of time. There's something poignant about the passage of time in the Pioneer story. Pioneer 10 was launched in 1972. That was 54 years ago, as of 2026. It's been in space for over half a century. When it was launched, the Vietnam War was still ongoing. The Watergate scandal hadn't happened yet. The internet didn't exist. The personal computer hadn't been invented. When the last signal was received from Pioneer 10 in 2003, the world was a different place. The internet was ubiquitous. Personal computers were everywhere. The world had changed enormously. And yet Pioneer 10 was still out there, still the same spacecraft, still traveling through space. In a way, Pioneer 10 is a time capsule. It carries with it the technology and the values of the early 1970s. It carries Chuck Berry's Johnny B. Good and Mozart's Magic Flute. It carries images and messages from humanity in 1972. It's a message from a past era to a future one. When or if the pioneers are ever found by another civilization, they'll be carrying messages from humanity's past. They'll be showing what we valued, what we thought was important, what our music and art and science meant to us. The scale of the achievement. Let me try to convey the scale of what the pioneers achieved. Pioneer 10 traveled about 12 billion kilometers from Earth. That's 80 times the distance from Earth to the Sun. To put this in perspective, light from the Sun takes 8 minutes to reach Earth. Light from Pioneer 10 takes over 11 hours to reach Earth. If you were on Pioneer 10 and wanted to send a message to someone on Earth, that message would take 11 hours to arrive. The response would take another 11 hours. A simple yes or no question would take at least 22 hours to answer, and yet we communicated with Pioneer 10. We sent it commands. It executed them. It reported back. We did this for 30 years. The distances involved are hard to comprehend. They're so large that we have to use abstract numbers. 12 billion kilometers, 80 astronomical units, 11 light hours. But the reality is that humans built a machine, sent it on a journey, maintained communication with it, and received data from it across distances that beggar the imagination. It's a remarkable achievement. The fate of the pioneers. We don't know what will happen to the pioneers. Pioneer 10 and Pioneer 11 are still out there somewhere in the void. They're still traveling, still carrying their instruments and their golden records. At their current speeds, Pioneer 10 will reach the nearest star, Proxima Centauri, in about 73,000 years. That's an unimaginably long time. Human civilization as we know it has only existed for about 10,000 years. The pioneers will be traveling for 7 times longer than human civilization has existed. Eventually, Pioneer 10 might leave the Milky Way galaxy. In 1 billion years or so, it might reach intergalactic space. It might encounter another galaxy. It might travel to the edge of the observable universe. Or it might not. It might drift forever, never encountering anything, never being found. But it will keep traveling. It will keep carrying its message. In a sense, the pioneers are immortal. As long as the physical universe exists, the pioneers will exist. They might be broken and non-functional, but they'll still be there. Still traveling. They're a piece of humanity that we've sent out to live forever. It's interesting to compare the pioneers to other space missions. The Apollo missions were about reaching a destination and returning home. We sent astronauts to the moon and they came back. It was a round trip. The pioneers are different. They're about leaving and not coming back. The Voyagers, which came after the pioneers, are similar. They're on one-way journeys. They're designed to go far and keep going. But the Voyagers are bigger, more sophisticated. They have more instruments. They were built with better technology. The pioneers were earlier. They were smaller. They had less power. They had to be more clever about how they used their resources. In some ways, the pioneers are more impressive because they accomplished so much with so little. The Voyagers carried the golden record further. They've reached interstellar space. Voyager 1 is the farthest spacecraft from Earth, but the pioneers came first. They proved it could be done. The decline and fall. Eventually, all spacecraft fail. It's inevitable. For the pioneers, failure happened slowly. The power from the radioactive fuel gradually decreased. The signals gradually weakened. Scientists at Mission Control watched as the signals became harder to detect. They knew what was happening. They knew that eventually the signal would fade completely. For Pioneer 10, the last signal came in 2003. Mission controllers checked and rechecked. Could they still detect the signal? Each time it was fainter. Each time it was harder to be sure they were actually receiving data and not just noise. Finally, it was gone. The signal was too weak to detect. Pioneer 11's signal had faded earlier, in 1995. When the last signals were received, there was a sense of finality. These spacecraft that had been humanity's ambassadors to the outer solar system were gone. But they weren't really gone. They were just silent. There's something profound about the silence. For 30 years, Pioneer 10 transmitted. It sent data. It sent telemetry. It sent the story of its journey. And then it stopped. The silence that followed is the silence of space. The silence of a machine that has done its job and now drifts silently. It's a poignant silence. It's the silence of saying goodbye. Carl Sagan wrote about this silence. He talked about the moment when a spacecraft signal fades, when we can no longer hear from it. He called it a kind of death. Not a death in the biological sense, but a death in the sense of losing contact, of saying goodbye. But the pioneers aren't really dead. They're still out there. They're still traveling. They're still carrying their instruments and their golden records. They've just gone silent. There's something beautiful about that. There's a dignity in it. The pioneers finished their mission and then fell silent. They did what they were built to do, and now they drift. Here's a question that haunts me. Will the pioneers ever be found? The odds are vanishingly small. Space is vast beyond comprehension. The pioneers are tiny. The chances of another spacecraft or another civilization encountering one of them are almost zero. But they're not zero. In 73,000 years, Pioneer 10 will reach Proxima Centauri. If there's a civilization there, they might detect it. They might recover it. And if they do, they'll find the golden record. They'll see our pictures. They'll hear our music. They'll read our message. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. What will they think? Will they understand what we were trying to say? Will they understand that we were reaching out? That we were lonely? That we wanted to make contact? Or will they just see an artifact, a strange object from a distant time and place? We don't know. We can't know. But the fact that we sent the message anyway, that we sent it even knowing that it might never be found, says something about us. It says we're hopeful. It says we believe in the possibility of contact. It says we think our existence is worth preserving. The meaning of the missions. What do the pioneers mean? They mean different things to different people. To scientists, they mean a revolution in our understanding of the solar system. They mean the beginning of planetary exploration. They mean data that we're still analyzing decades later. To engineers, they mean proof that we can build spacecraft to last, that we can send machines on journeys that span decades and they'll keep working. To philosophers, they mean a statement about human nature. They mean that we're explorers, that we reach out, that we're willing to send things into the unknown. To poets and artists, they mean wonder, They mean the beauty of exploration, the poetry of humanity sending golden records into space. To ordinary people, they mean a sense of awe, a sense that humanity is capable of extraordinary things, a sense that we're not confined to Earth, that we can reach out and touch the cosmos. The pioneers mean all of these things and more. The ultimate purpose. If I had to distill what the pioneers mean into a single statement, I would say this. The pioneers are humanity's way of saying we existed, we were here, we thought and felt and created. We were curious about the universe and we reached out to explore it. They're a message in a bottle, except the ocean is the cosmos and the bottle might drift forever. We don't know if anyone will ever find the pioneers. We don't know if they'll ever be discovered. The odds are against it. But we sent them anyway, because exploration matters, because curiosity matters, because the act of reaching out into the unknown matters, even if no one ever hears from you. The pioneers are proof that humanity values these things, that we're willing to spend resources and effort on exploring, on wondering, on reaching out. In a universe that's vast and indifferent, the pioneers are a small gesture of defiance. They're humanity saying, we're here, we matter, our existence has meaning. The long voyage continues. Somewhere out in the void, Pioneer 10 and Pioneer 11 continue their journey. They're traveling at speeds of about 10 kilometers per second relative to the sun. That's 36,000 kilometers per hour. That's fast, but in cosmic terms, it's slow. It will take them tens of thousands of years to reach the nearest star. But they'll get there eventually. Or maybe they won't. Maybe they'll drift forever in the void, never encountering anything. But they'll keep traveling. They'll keep carrying their golden records. They'll keep being ambassadors from humanity. The pioneers have become part of the cosmos. They're no longer spacecraft. They're artifacts. They're monuments. They're humanity's gift to the universe. The pioneers teach us lessons that are relevant today. First, they teach us that long-duration exploration is possible, that we can build things that last, that we can accomplish our goals even with limited resources. Second, they teach us that exploration has value in itself, that we don't need immediate practical returns, that the pursuit of knowledge is worthwhile. Third, they teach us that we're capable of remarkable things, that we can overcome technical challenges, that human ingenuity can solve problems that seem insurmountable. Fourth, they teach us about cooperation. The pioneers were built by hundreds of engineers and scientists working together. They represent the collective effort of humanity reaching out. Fifth, they teach us about thinking long-term. The pioneers were designed to last decades. The engineers and scientists involved understood that they were building something that would outlast them. They were thinking about the future. These are lessons we need. Today we face challenges that require long-term thinking. Climate change, resource depletion, the need for sustainable energy. The pioneers remind us that humans are capable of long-term planning, that we can build things that last, that we can accomplish remarkable things if we work together. The pioneers themselves may be silent now, but their legacy lives on. Every spacecraft that explores the outer solar system builds on what the pioneers taught us. The Voyagers, which reached interstellar space, used technology pioneered by the pioneers. The Galileo spacecraft, which orbited Jupiter and studied its moons, used the data from Pioneer 10 to plan its trajectory and choose its instruments. The Cassini spacecraft, which orbited Saturn, was influenced by Pioneer 11's discoveries. The New Horizons spacecraft, which flew past Pluto, studied systems that the pioneers had explored. every mission that travels beyond Earth carries something of the pioneer spirit, the desire to explore, the willingness to undertake long journeys, the commitment to pushing the boundaries of human knowledge. The pioneers proved that it could be done, and because they proved it, everyone after them could do it better, farther, with more data and more understanding. The human element. What strikes me most about the pioneers is the human element. These weren't soulless machines. They were built by people. They reflected the values and the dreams of the people who built them. The decision to include a golden record was fundamentally human. It was Carl Sagan's idea. It came from a place of wonder and a desire to communicate. The engineers who designed the spacecraft, who calculated the trajectories, who built the systems, they were motivated by more than just technical challenges. They were motivated by the dream of exploration, by the desire to reach out. The scientists who analyzed the data, who interpreted what the pioneers were telling us about the solar system, they were driven by curiosity, by the desire to understand. The mission controllers who listened to the signals from the pioneers, who received the data year after year, decade after decade, they were maintaining a connection. They were keeping the conversation going. All of this is deeply human. The pioneers are technology, yes, but they're also a reflection of human values and human dreams. The ultimate fate of everything. Looking at the pioneers, we're confronted with big questions about the ultimate fate of the universe. The pioneers will eventually decay. The atoms that make them up will be scattered. The radioactive fuel will be depleted. Over billions of years, the material will break down. But the message will persist. The structure of the golden record will persist. The information encoded in it will persist. In a sense, the pioneers are fighting entropy. They're creating order and meaning in an indifferent universe. They're saying this matters. This information is important. Eventually, entropy will win. Everything decays. Everything falls apart. But for a time, for thousands of years maybe, the pioneers will persist. They'll carry their message. They'll represent humanity's reach out into the cosmos. That's all we can ask. Not immortality, but a while. A span of time in which we matter, in which our existence makes a difference. The pioneers give us that. In the end, the pioneers are about hope. Hope that we're not alone. Hope that someone will find our message. Hope that our existence is significant. But more fundamentally, they're about hope in humanity's potential. Hope that we can achieve remarkable things, that we can explore and discover and create. The pioneers prove that hope is justified. We built machines that have traveled farther than any human has ever traveled. We maintained communication with them across billions of miles. We learned from them. We were changed by them. We accomplished all this because we believed it was worthwhile, because we valued exploration and discovery, because we hoped we could reach out and touch the cosmos. And we did. The pioneers are out there, still traveling, still carrying their golden records, still the farthest artifacts from Earth. They're monuments to human curiosity, to human courage, to human hope. And as long as they're out there, a piece of humanity is out there too. A piece of us has reached the stars. If someone reads this in the future, decades from now, or centuries, or millennia, I want them to understand what the pioneers meant. They weren't just spacecraft. They were expressions of hope. They were humanity saying, we believe in ourselves. We believe in exploration. We believe that our existence matters. The pioneers failed in many ways. They never found alien life. They never made contact with another civilization. They never came home. but they succeeded in ways that matter more. They expanded our understanding of the solar system. They inspired generations of scientists and engineers. They captured the imagination of humanity. And they're still out there, still traveling, still carrying their message. The pioneers remind us that we're capable of remarkable things, that we can dream big, that we can reach out into the unknown and do it successfully. In a time of uncertainty and division, the pioneers are a beacon. They remind us that humanity is capable of cooperation, that we can accomplish things that seem impossible. The pioneers teach us that exploration matters. That curiosity is a fundamental human value, that the pursuit of knowledge is worthwhile, even if we never see the immediate results. Remember the pioneers. Remember what they achieved. Remember what they mean. And remember that somewhere out in the cosmos, they're still traveling, still carrying humanity's message to the stars. That's a beautiful thought. That's a legacy worth preserving. The pioneers are humanity's gift to the universe. And the universe, I think, is better for having received